Okay, let's look at another example about what can go wrong when you're trying to apply the multiplication principle. So here's an example. How many 4-digit numbers with the digits 1, 2, 3, 4 are there where every successive digit differs by 1? Here are two examples. 1, 2, 3, 2 goes up by 1, and down by 1. 3, 4, 3, 2 goes up by 1, down by 1, and then down by 1. Every successive digit differs by exactly 1. One way we might think would be a natural way to count these objects is to see this as a sequence of choices. Choose what the first digit is. Choose what the second digit is. Choose what the third digit is. Choose what the fourth digit is. And as we start, we recognize the first digit could be any of the 4 numbers, so there are 4 choices for the first digit. But we soon start to realize that we have a problem. The number of choices for the second digit depends on the first digit. If the first digit is a 1, it can only go up to 2. However, if the first digit is a 2, then there are 2 choices for what the second digit can be. You can either have a 3 or you can have a 1. Because the number of choices depends on the previous choices, you cannot apply the multiplication principle. You'll need another technique. And luckily I have one of those for you in my arboretum. They are called decision trees. When what you are counting depends on a sequence of choices, you can use a decision tree as a visual method to keep track of those choices. And this does not require that the choices are independent. So how do you build a decision tree? This tree is drawn from left to right in stages. At each stage, new branches are drawn that correspond to each choice. Each of those choices is a decision, and that's why it's called a decision tree. Be aware that there might not be any choices available, in which case no branches are drawn at that stage. The branches that survive to the end of the tree correspond to the set of all valid sequences. Hey, we've enumerated all the possibilities. When you have a list of possibilities, you count them, and that will answer the question. From our example on the previous page, we see that the first letter can be 1, 2, 3, or 4. Now, based on what the first letter is, there are different numbers of choices. If we start with a 1, we must choose a 2, and we build a branch corresponding to that decision. If the first number is a 2, there are 2 choices. Either the second digit is a 1, or the second digit is a 3. If we have a 3, then the second digit can either be a 2 or a 4. And if the first digit is a 4, then the second digit has to be a 3. We then build the next stage of our tree. If the first 2 stages are 1 and 2, the next number can either be 1 or 3. But if the first 2 digits are 2 and 1, then the next digit has to be a 2. We continue making the decisions. We fill out the rest of this stage by adding branches for each valid decision. And then we have one more stage to do. We've now come up with every single possible word that satisfies the desired conditions, so all that's left is to count them. And so there are 16 words where each consecutive number is off by exactly 1. This view also gives us some additional intuition about why the multiplication principle works. If the number of choices are independent, then the number of branches at the next stage would be a multiple of the number of branches at the previous stage. So now we have 2 principles. We'd like to combine them. You may be in a situation where you have to apply both principles in the same problem. And the order in which you do that depends on the situation involved. Let's go back to making some outfits. You look in your closet and you see that you have 4 red tops, 5 blue tops, 2 gray bottoms, and 6 black bottoms. In how many ways can you make an outfit consisting of a top and a bottom? To approach this question, we recognize that an outfit is made up of a top and a bottom, and so we'll have to figure out how many tops there are and how many bottoms. A top can be red or blue, and a bottom can be gray or black, and so for those we need to apply the addition principle. 4 plus 5 total tops, 2 plus 6 total bottoms, and now our outfit is a sequence of a top and a bottom, so we apply the multiplication principle, and we get 72 total outfits. Let's answer a different question relating to outfits. Because of your personal style, you want an outfit that consists of a red top and a black bottom, or a blue top and a gray bottom. in how many ways can we do that? In this situation, a better way to break down your set of outfits is to think of these as an outfit of type 1 or an outfit of type 2, and then count each of those using the multiplication principle. If your outfit needs to be red and black, there are 4 times 6 choices, 24. And if the outfit has to be blue and gray, there are 5 choices for a top, 2 choices for a bottom, or 10. Then we add those numbers together to get a total of 34 different outfits. The first answer was 72, this is 34, and we might expect that this number is smaller because all of the outfits in the second question are valid outputs for the first question, but not vice versa. All right, good luck with all your counting, and I'll see you again next time.